Okay, this is lesson 6.5. We're going to be looking at the fundamental theorem of calculus again, but the second part of it. And then we'll also tackle the idea of how to integrate involving natural log functions. Okay? So instead of me just telling you what the fundamental theorem of calculus is, the second part, let us see if you can figure it out using this example as an informal guide. So I'm going to give you this. Number one, this is an integral. It's a definite integral because 10 and x are limits. And I'm saying take the integral of this, of the f prime t dt function. So the integral of a derivative, of course, is just the function. So I'm just going to use f of t. And then we're going to evaluate this from x and 10. Doing so, I guess I will plug in x wherever I see t. And then I'll also plug in 10 wherever I see t, and that is my result. So f of x minus f of 10. Perfect. Now looking at number 2 here, it says, ooh, take the derivative of ddx. Take the derivative of this integral. Well, this integral so happens to be number 1. So really, I'm asking you to do the following. Take the derivative of the answer to number 1, which would be f of x minus f of 10. So what is the derivative of f of x? So if I apply the derivative to f of x, what do I get? That's correct, just its derivative, f prime of x. And then if I apply the derivative to f of 10, now f of 10 is just some value or a number. So the derivative of a number must be, you got it, 0. And so ultimately this is just equal to f prime of x. So that's pretty much what I had when I started, except I replaced the t with now the variable x. And so this is what the second fundamental theorem of calculus says. For any constant a, okay, any constant, the derivative, so ddx, of the integral from the lower limit of a to the upper limit of x of a function f of t dt is just the actual function itself, except I replace the t with the x. And that is the fundamental theorem of calculus. Taking the derivative of the integral just gives you the same thing. You just replace the dummy variable t with the variable x. Okay? The key that I want you to remember is that the constant here has to be the lower limit. Okay? Constant must be lower limit. Okay? If it isn't, so as a note, if you had something like this, x to a of f of t dt, you could have done the same process. What you would have found is you would have got the negative of the answer. So this is really the same thing as taking the derivative of, and if I were to change the a to the x like this, that just makes this whole thing here negative. Okay? So your answer in the end would have also been negative f prime of, sorry, in this case not f prime, in this case just f of x. Okay? Alright, so constant must be lower limit for this to work, otherwise it's what I just wrote down there. Okay, now that is the basic one. So I'm going to ask you to do something a little bit different. What happens if the variable is no longer x? What if I change it to something a little bit more complicated, like x squared, or if I had variables in both? So let's do the same process and see what we get. The integral of a derivative is just the function itself, so f of t. And I'm going to evaluate this from x squared to 0, which means I have f of x squared minus f of 0. Nice. Example number 4 then says, hey, let's take the derivative ddx of, what we just had in number 3. So that's the same thing as take the derivative of my answer to number 3. So that's f of x squared minus f of 0. And now what happens when I ask you to take the derivative of f of x squared? Well, if you said the derivative should be f prime of x squared, you are Almost right. What did you forget? Yes, this is a function within a function. So, chain rule time. Don't forget the derivative of the inside, which is 2x. Okay, star that. Chain rule. And then if I were to take the derivative of f of 0, well, f of 0 once again is a value or a number. The derivative of a value, number, constant would just, of course, be 0. So your answer here is just f prime of x squared, and then don't forget the extra factor of 2x. Beautiful. Okay, number 5. Yes, same kind of idea. So the integral, of course, is just the function f of t. This time I'm plugging in 2x and x cubed, so I get f of 2x minus f of x cubed. And look at number 6. It's the derivative of, yeah, the exact same thing as number 5. So let me write this nicely here. d dx of the answer to number 5, which is f of 2x minus f of x cubed. Now, what happens when I take its derivative? Well, the same thing as number 4. F prime of 2x, but don't forget this is a function within a function. Yes, thank you. If you said in your mind or out loud to the screen, yes, an extra factor of 2. Bravo. And then when I take the derivative of f of x cubed, yes, that becomes the derivative of x cubed function. But yes, once again, we have a function within a function. Hello, chain rule, and the extra factor of 3x squared. So this gives rise to the second fundamental theorem, the chain rule version. And this is the one I actually like to memorize because it encompasses the previous one as well. If now your limits are no longer just regular x and a constant, now they are u and v and they are functions, then what that says is taking the derivative of the integral of this f of t dt, you actually plug in the upper limit, but don't forget an extra factor of e prime and y. Yes, chain rule. And you're minus f of u with another extra factor of u prime. Once again, chain rule. Okay, so when you have a function in your limits and they're not equal to x, hello, chain rule. Okay, so continuing with this, can you now find each of the following without actually doing the whole process of integrating and then taking the derivative, because it takes too long? Number 7. I mentioned this earlier. Look at this. The x, the variable, is in the bottom, but it should actually be in the top. So what do I need to do these things? I need to switch them. Yeah, so I need to switch them. And if I switch them, I get a negative that comes out, right? So the negative of 0 to x of 2t minus 3 dt. And then I know that the derivative and integral just cancel each other out using the second fundamental theorem of calculus. I'll just get 2x minus 3. But wait, I still have this negative. So don't forget to apply it. So I better put a negative in front. And that's it. Okay, how the next one? Oh, interesting here. Yes. I'm plugging in, numbers this time. What do you think happens when I take the derivative of a number? Yeah, it's just going to be 0. So note here, notice the lower and upper limit are numbers. So when I actually take the integral of whatever function, this will actually equal to a number. And then of course the derivative of a constant, yeah, that is 0. Cool. Okay, how about number 9? Yes, it's time to, This is the chain rule version. So what does the chain rule version say? Yeah, we should just plug in x cubed wherever we see t. So get x cubed squared plus 2 times x cubed. And that would be my answer, except I need to multiply this by the derivative of the upper limit, which would be an extra factor of 3x squared. That once again is applied to both those terms inside. Okay. All right, and number 10. Ooh, this is an interesting way of writing things. I've got a function here, and I want you to find the derivative. So this is really me saying take the derivative of, so this is the same thing as the derivative of 0 to 3x squared, 1 minus t squared, t dt, which is pretty much like example number 9. So all we have to do is wherever we see t, replace it with 3x squared. And then don't forget the extra factor. Yeah, an extra factor of the derivative of 3x squared, which in this case is just 6x. Okay? So that concludes our fundamental theorem of calculus, the second part. And now, for the remainder of this lesson, we're going to quickly look at differentiation and integration of the log function. And we know that they are inverse operations. And we also know from before that the derivative of natural log of absolute value of x is 1 over x. Then if we reverse it, yeah, we get the integral of 1 over x dx is just the natural log of absolute value of x plus c. Okay, and that's what you need to memorize here. And then don't forget, if you have a function within a function, so natural log of u, you have to make sure there's also u prime involved, because if you do, then we can just say that this equals to the natural log of the absolute value of u instead. Okay? So regular version, kind of like the chain rule version over here. Okay. Now, just a quick note, I don't know if you remember when we did the derivatives of lns, but it was true that both the derivative of natural log of 1 over x, the derivative of natural log of x is 1 over x, and the derivative of the absolute value of x is also 1 over x. So why do we, when we take a look at the integral, have to give an answer that has this absolute value sign? Why can't we just use the regular x? Well, it's because the domain of natural log requires this. Okay, the domain of natural log requires the absolute value sign. Because if it doesn't, or if it's not there, I could have like a negative, and I can't really take the ln of a negative number. So to put the absolute value there, I guarantee that I will actually have something that can be evaluated. Okay, so let's go ahead and do some integration. Here we go. Oh, this is not 1 over x, but it's really close, because I can take out a 3, and that will be then the integral of 1 over x dx. And I know that that's equal to the natural log of, don't forget, absolute value of x, and then yes, plus c. Good. And you're thinking number 12, I don't see anything that looks like log here. True, true, true. But if you actually did some U-Substitution, or the reverse chain rule method, I don't know which one you like, but I'm just going to use U-Substitution here. And I'm going to solve for dp. So du, I'm going to quickly skip 2 steps, or skip a step. So du divided by 2p is dp. Why is this important? Because now if I make the substitutions, let's see what I get. P, now it's not p squared plus 1, but u. And then dp is the same thing as du over 2p, which is great, because the p's then divide out. That 2 in the denominator I can take out into the front. And look at this, 1 over u du, which is really the integral of 1 over u. Yeah, it's just natural log. So the natural log of u plus c, and then I'll make that final resubstitution. And of course u was p squared plus 1. And there you have it. Okay. And once again, if you did reverse chain rule, it might have been faster. It works too. I think for reverse chain rule, just for those of you who did it, you would have had to put a 2 here, and then you had to put a 1/2 in front. Okay. Alright, secant squared x over tangent x. Yikes! Trig. I did not like trig. Oh no. If you really have no clue how to start this, I hope maybe an inspiration of u might help. If I let u equals to tangent x, I hope you remember that du dx is just the derivative of tangent. Secant squared x. Oh, that's beautiful, because dx just equals to du over secant squared x. I like this, I like this, I hope you do too, because when I make my substitutions, something beautiful happens. Tangent is now u. Dx is now du over secant squared x. Bye-bye, bye-bye. Look at this beautiful integral. Yes, our favorite natural log. And then I will make the replacements, and voila. Yes, I speak French. Well, not really. Here is our answer. Ta-da! And once again, if you can use that reverse chain rule method, you should be able to see this right away and get the answer a little bit faster. But nonetheless, I'm just practicing U-Substitution, because I actually think it's a little bit more methodical. Okay. I'm going to ask you to try 14 and 15 as well, and I'm going to give you a hint that you will need to use U-Substitution or reverse chain rule for all these. So I've got enough examples. I think it's time for you to practice. So I'm going to ask you to please pause the video now and work on them yourself, and then unpause the video to come back and double check your answers here too. Okay? All right. Pause. I'll actually do both, okay? Reverse chain rule, and I'll do U-Substitution, just for those who like reverse chain rule. Why is this nice? Because if I let u equals to ln x, I can see that, hey, 1 over x is my derivative. So this is where I can remove it, and then the integral of something, and this would be something to the power of 1, would be, using the power rule, something squared over 2 plus c. Okay? Those of you are like, whoa, that was just magic. Let me use the U-Substitution way. Sure. U equals to ln x. Du dx is equal to 1 over x. I can then solve this. X du equals to dx. Then I will make the substitution. I get u over x, and then dx is x du, which is great because look, that divides out, and look, I have u du, which is pretty much what I did before. Then the integration of u du is just u squared over 2 plus c. And so natural log of x is what I replace it with, plus c. Okay. 15, if you can do either way again, I'll just quickly use U-Substitution. Then I can then make my substitutions. Here we go. U cubed dx is negative x du. Goodbye, goodbye x. 1 over u cubed du with the negative in front. Ooh. And then that is the same thing as, yes, u to the negative 3 du. Good old power rule. Add 1 to the exponent. Divide by the new exponent. Don't forget plus c. We'll simplify. Oh, too many negatives here. Ah, too many negatives. That's okay. And I can make my replacement. U was just 2 minus natural log of x to the negative 2 plus c. There you go. All right. All right. All right. And if you thought we were done, I'm so sorry. A few more examples here for you. Okay. We never did the integral of these weird things, cotangent and tangent, so let's do them now. But the key for doing these ones is to rewrite the fraction using a trig identity, using a quotient identity, yes. So cotangent, I hope you remember, is the same thing as cosine x over sine x, okay, from your pre-calculus days. Now, you can use U-substitution or that reverse chain rule, either or, and you should be able to get the answer. Okay, if I were to use reverse chain rule, look, the derivative of sine is cosine. So I can just go, hey, goodbye. And then this is 1 over something, like 1 over u. And the integral of 1 over u is just, yeah, natural log of whatever that thing is, u. So that thing is sine x, and you are done. But if that was way too, like, weird, then once again, if I let u equals to sine x, that same process occurs. The derivative is cosine of x. I'll solve for dx. And then I will make the substitutions. So let me make the substitution again. The substitution would be cosine x. But instead of sine x, it'd now be u. And then instead of dx, it'd be du over cosine x. And look at that, you still get the same thing as 1 over u du, which of course equals to the natural log of u. And of course, I can put in the u factor, which was sine x, and we get the exact same answer as above. Okay, so once again, reverse chain rule, if you can see it, great. If you can't, use substitution, a little bit longer, but it always works. Okay? All right, you do number 17, please. Go. Sine x over cosine x. Good. I'll use the U-substitution way this time. Let u equals to cosine x, so du dx is negative sine x. Solving for dx, you get du over negative sine x equals to dx. Making the substitutions now, we can then make this equal to sine x, cosine x, wait, that's u, dx, wait, that's du over negative sine x. That's great, those divide out. I got this negative in front, no worries. Just like a constant, natural log of u plus c, no worries. I can then replace the u with cosine of x, no worries, because I am done. And by the way, that's where we get these lovely formulas from. Number 16, number 17. And yes, you should memorize them. And also their chain rule equivalents, where if I replace x with u, you need that extra factor of u prime. Same thing here. You need that extra factor of u prime. So for number 18, instead of using u substitution, I'm going to see if I can relate tangent 2x dx to, I guess I should highlight this in green, okay. I'm going to relate it to this here. Notice that my u function is 2x, so I need to have a u prime, so I really need a u prime. How can I write in a u prime? Well, the u prime is number 2, but I can't just obviously do that. That changes the question. I have to balance that 2 out by multiplying it by a half, because now, once again, a half times 2 just gives, oops, don't erase it, or don't write it out. Half times 2, that just gives me 1. Now it's equal to my original equation. This is great because now I can just quickly use that fact, the reverse chain rule. Ooh, disappear. And the integral of tangent is just, yes, the negative natural log of the absolute value of cosine, not u, but 2x in this case, and then of course plus c. And so if I wanted to write this a little bit nicer, I can combine, of course, the negative and the 1/2, these two things, to write down negative half times the natural log of the absolute value of cosine 2x plus c. And if you really want, yes, you should put brackets around the 2x because the cosine is of the entire function 2x. And there you have it. Okay? Once again, a lot of material in this section. Okay? Two large concepts that you do need down. So go ahead, please, and practice, practice, practice. Okay? Come back for lesson 6.6. It's another doozy, okay? So this chapter, lots and lots of skills. Gotta practice.